Hi, in this video, we'll be going through first order linear differential equations. And so, in the previous video, we went through what are known as separable equations, and it is actually a form of a first order linear equation. So, a separable equation, you can recall it has some form like the following. And if we consider a more general form where the coefficients of a and b are, instead of constants, you replace them with functions of t, then it can be written in this way, and this is known as the standard form of the first order linear equation. So for the standard form, you must remember that the coefficient of the derivative term is 1. Then a more general one is you have a term here, but you can easily make this into the standard form by dividing by pt, by the function p. So how do we solve such equation? Well, we'll come up with a method later on, but let's take an example to see how the method works first, or how we'll think of the method. So we solve the differential equation of the following form, and what do we recognize? Well, we recognize that the derivative of this function is this left hand side. That's what you need to recognize, because you differentiate 4 plus t squared, you get 2t. So actually you can rewrite this whole part as this one derivative, and in that case then this is a derivative of t. So when you integrate with respect to t, it gets like cancelled out in a sense, so you're only left with this function. So it can be rewritten as this, and then you can now integrate both sides with respect to t. So this side you get 4 plus t whole thing squared times y, and for the other side is 2t squared plus c. And as a result, we can just divide by 4 plus t squared, so y equals to 2t squared over 4 plus t squared plus a constant over 4 plus t squared. And this is the general solution of the equation. So you can see what we want to do and what we try to achieve is this left hand side, because it has dy dt and it has a y here. In a sense, you're using the power rule to differentiate y first, then later you differentiate the t term. So then you can write it as a single derivative of some function. That's the idea. And with that idea, let us consider the following equation. So we got dy dt plus half y equals to this function. So what we want is we want to multiply a function mu to the equation, so that this equation becomes a derivative of mu times y. As a result, this indicates that the d mu dt is this half mu. And this means that, because, okay, so what is the only function that you differentiate to get back itself with some constant multiple? That would be the exponential. So solving this, you get that mu is e to the power of half t over 2, I mean. And so if we multiply mu as e to the power of t over 2, we actually get the function that we want, so that it can be reduced to this derivative only. And when we integrate this with respect to t, this part gets cancelled out, we're left with this function. And when we integrate this, we can do it so, and you'll get 3 over 5 e to the power of 5t plus over 6 plus c. And then we just divide this out and we get a general solution. Then this is how the direction field looks like. So this function that we choose that helps us in solving the first order linear equation is known as an integrating factor. And in general, if we have a general first order linear equation, then we want to determine an appropriate integrating factor. we just multiply this mu throughout, and the idea is to always get a single derivative in the end. So this mu will always be of the form exponential integrating the function p, where p is the original, the coefficient of y. But if you understand this idea, then you can always understand how to get the integrating factor without memorizing that it equals to e to integral pt dt. And then this will be the formulas, and you can simplify to this. But again, if you understand how to derive it, this won't be necessary. So in example 5, we'll take a look at how we can apply this integrating factor one more time to better understand what's happening. So we are given this general equation with an initial condition. We first have to convert it to standard form. So it's divide out by the coefficient of the derivatives to get the coefficient we want here. Then our integrating factor is e to the power of integrating t over 2 dt, which gives us exponential t squared over 4. What's one thing to note is the integrating factor, when you integrate the power here, you don't need to add a constant, because actually the constants will be cancelled out if you carry on. So you only need a single integral. And then we multiply it throughout the equation. And this allows us to say that the left hand side is the derivative of et squared over 4y. So when we integrate this side, we integrate the whole thing, it becomes et squared over 4y, integrating this whole thing plus a constant. And if we carry on, we actually see that the integral cannot be evaluated, and so we can just leave the answer as the following. And if we want any values, then we just sub into the initial condition and we'll be okay. So this is the example. It's just to illustrate that the solution may be sometimes left in integral, and there might not always be an explicit solution. But we can use online tools to help us still plot the graphs of this solution, just to see the behavior of it. So that's all for this video. I hope you've enjoyed this video where we went through how to solve first order linear equations. In the next video, we'll be carrying on our journey into ODEs and more techniques. See you again. Bye.